Okay, since we are now 5:10, we welcome Felix to the last talk. So our last talk today is by Felix Krahmer, and his title is Sigma Delta Quantization and Digital Halftoning of Images. And well, he will talk to us now.
Oh, I don't know what happened. Thank you. Okay, now it's okay? Yes. So what I said is it's work with my very talented postdoc, Anna, and it's about halftoning. And the idea is that natural images have a continuous grayscale, but one can only print in black or white. This goes back to even the old days when I was really using the needle printing and so on. It's even relevant for color representation in digital form, because you also have this 0 to 256 scale, but this is not the topic of this talk. But the idea behind why this is actually useful is that one aims to exploit a smoothing operation inherent in visual perception. One only needs that a smooth version of the representation approximate a smooth version of the image. So there's, in the mathematical literature, people have often approached this from the viewpoint of what would be called analog halftoning. So they represent a continuous image by a finitely many Dirac deltas or measures supported on more complicated curves or something like this. Locations of the masses are arbitrary in the continuous domain. And but from the applied point of view, maybe you want to go maybe even a step further, because like putting Dirac deltas at arbitrary locations is not something that you can implement. What one would rather want in applications is something called digital halftoning that is operating on a discrete pixel grid, representing the image via the use of white and black pixels on the grid. And so a wide variety of methods are available, but not much mathematical theory. So with this, I would like to thank Sinan, who is in the audience, because when I was a PhD student a long time ago, he introduced me sort of to this problem and the connection to the research work I was doing at the time. I couldn't make anything out of this, so I needed Anna for this to actually make some progress on making this more rigorous. So to give you, if you haven't seen this before, so I mean, I'm giving it away here, but I don't know if you know which one is which. Here, I think it may be visible here that the picture on the right is the halftone image. You can see a little bit of the dots in the middle of the eye, but on the picture that's just using black and white dots, and then the picture on the left is the grayscale image represented on the computer screen. So here mathematically we are mapping the interval from -1 to 1 as the values of this image to ±1 here. So for reasons that we will see later of symmetry, we are going to -1 1 rather than 0 1. Of course, it's equivalent. Okay. So how does this work if people are doing, how was this picture that you just seen computed? So this picture was computed using so-called Floyd-Steinberg error diffusion scheme. So what happens here is you take, in order to calculate whether the blue dot is black or white, you take some state variables that are computed for all these red locations. You average them with some strange looking weights, and so then what you get is an expression like this. And the point is that here you get a new, like with this averaging the blue when you get a new state variable v here, averaging these red state variables. And then whatever you get here, you're plugging into the sine function, and that gives you the ±1. So this may seem arbitrary for now. What you should take here is that for some reason, you're diffusing the error, so you're keeping track of some accumulated error that sort of spreads from the top left to the lower right through the image. Okay. So why does this work? As I already said, the smoothing operation inherent in visual perception performs a local averaging, and the idea then, and that's sort of what the error diffusion scheme does, you need to pick black and white values such that the local averages agree with the gray value more or less. And a model that we will use as a motivation here, and that's where the connection to sigma delta comes into the game, is that the smoothing can be approximated by low pass filtering. And so in this model, the problem boils down to finding a bit sequence such that this low pass content agrees with the band limited signal. And that would then be the smooth image. So this problem is, that's why I said, and I'm not taking credit for this. And this is something that also was something that Sinan pointed me to this work by Kite and others in an engineering conference, who just noted the correspondence between sigma delta and digital halftoning without sort of, as far as I remember, without using it to any benefits. More like, okay, this is a way of understanding maybe a little bit what's going on, but at least I don't recall that this had sort of some positive effect on the quality or something like this. So the goal of this talk is to change that and to go a step further, to study error diffusion techniques from the perspective of 1-bit sigma delta quantization and also actually improve them. So this is to get, let's be a little bit more formal. We said we have the model that our human visual system acts as a low pass filter. This is the model for now. This we will see later, like we will take it to its limit. We will see that it's not correct by making a comparison at the end. But the point is that it still can serve as a good motivation for designing schemes. And the images then in this simplified model are then perceived as 2D low pass signals. So the signal model here is that of a band limited signal that basically says that the frequency support is in a square between negative omega/2 and omega/2 in both directions. So then what you can do, I think you probably know this in 1D, but you can do it just the same way in 2D. You can use Shannon sampling theorem in both directions. You now are sampling over the grid Z2, and you have a kernel of low pass type that is 0 in a certain region, and then 0 outside a certain region, and 1 inside a certain region, and then smooth a little bit in the middle of that. Okay, so I think that's what many of you are maybe familiar with. The notation-wise, what we're taking from here is that we can represent the continuous band-limited signal using a discrete sequence and of sample values, and this sequence we're calling yn. So the quantization map. So now what we want to do with this, we want to sort of take this representation and quantize it, in the sense that we want to map the sequence of samples that we've just seen as is completely representing the function to a sequence of quantized samples in -1, 1. So then the objective is then, okay, what are we doing this? When is this quant? I mean, we can certainly choose all q's to be 1. When is it good? So we are saying that, okay, we're having this, we're just taking the qn and putting them in the function in the position of yn. And what we want is that this resulting function is close to the original function. So the error that corresponds to the error that's written here on the bottom, EQ, which is you're just subtracting this original exact representation from the quantized representation. And if we are doing it perfectly fine, we're even adding the 1 over lambda squared that somehow fell down the slide somehow. So this is something where oversampling gives you potentially a better error. So I mean, this is something that I just dropped. Okay, so let's revisit the case that is most understood for this. Let me the 1D case. So how do we define such a quantization map? And that's the idea of sigma delta quantization. So we are just going along the lines in the recurrence relation. So keeping, like in some sense, doing something remotely similar to to what I have motivated in 2D. That's also how this correspondence was then motivated. And to just saying we're keeping track of some accumulated error. So here we are, the V naughts are the accumulated error. So you start with the true error, Y naught minus Q naught. That's the error that you're making with the first quantization. And then you're accumulating it. So you're taking, you're quantizing it somehow. And no, this is the error that you're doing the quantization. So you're keeping it and adding it to the error that you're having in the next step, and so on and so forth. And this can be represented using the finite difference operation that you see here on the right. And then you can actually relate the state variable also to the error that we have seen on the previous slide. Okay. The generalization that we will also use later on is that you can take this to higher bits, to higher order. So here you see this orange representation, delta Vn is Yn minus Qn, and you just take the finite difference to a higher order. So you take here, we have the first order finite difference. You just, I mean, why are we doing this is something that, like, the reason that this works is that the finite difference somehow interacts well with the smoothness of the function in the error bounds. So if you have a higher order finite difference, it interacts even better. So that's why it makes sense to look at something like the rth order finite difference here. In this talk, all we will go up to is 2. So we will not. So you can think of a second order finite difference here. So just to give you some intuition how the engineers would see it, they would think about this problem in terms of what they call noise shaping. The idea being that so they look at the noise, the quantization noise in the frequency domain, because this reconstruction formula that I've shown you can be interpreted as a low-pass operation. So that's why if you're looking at the full quantization noise, then and you know that you will be applying a low-pass operation, it's okay that you have large error for high frequencies, but as long as you have small errors for low frequencies. And this is what this picture shows. If you're just the first one, I didn't say what MSQ is, it's just taking the sign of each sample. Then you see the error spreads everywhere. And on the bottom, when you're doing the sigma delta that I've seen, it achieves exactly this. For small frequencies, it has a small error. And for high frequencies, it has a larger error. So when you apply a low pass filter, it makes the error small. So that's just to give you an intuition. And so just the next step to go from, I think I won't go too much into detail. This is some way to formalize it that goes back to Sinan, where you're going from this, when you want to do error bounds, it's advantageous to look at more general classes of filters rather than just delta to the n. But you just have a general filter H that you're evolving with, and I'll give you an example of that later on. And the most important thing is that the rth order nature of the filter now boils down to the fact that this new filter H has some rth order finite difference hidden inside. Okay. So that is this, and why we want to do this. So why we want to have this representations, because this function g that we've seen just shows up in the error bound. It's not so important to understand this error bound exactly right now, just to see that if we're having this representation and you're carefully designing the schemes in the way that we have seen on the previous slides, you can actually achieve competitive error bounds. So, and what you need to that is something that's called, and that's something that will be important later on. That's a concept that's called stability. So what could happen with the sigma delta quantizer is what is called positive feedback. So it means you have these state variables that are accumulating, so the voltage is growing and the circuit is exploding. And then, of course, also no error, like no good error bound is taking place here. And what you need for this is that this filter H in the one norm is less than 2. And this is something, then you have stable, but this is the thing that's very important. So what we need is that the L1 norm of our filter H plus the L infinity norm of our signal is less than 2. And this is a problem for images, as we will see, because what we will see is like if we want to do a higher order sigma delta, then h has to be in the L1 arm slightly larger than 1. And that means we have to restrict the images to be somewhat smaller than 1. But this is something that is not very natural, right? So if you have an image and you want to represent it, you want to use the full range. And I will maybe briefly mention how we deal with this by using a small trick later on. So, but let's just go through some ideas first. I mean, the first thing that you could do is if you don't know how to do 2D sigma delta, let's just do 1D row by row. Okay. And this, if we're having, if we're applying this for band limited signals, we get okay error bounds, because you can just get the error bounds line by line, and that's not a problem. But as soon it doesn't exploit the 2D nature at all. And also, if you look at the image that are resulting from this, it's horrible, right? You see these very strong line artifacts. You don't want to do this. So you could also try to do this, that you're doing a finite difference in both directions. So you're taking a delta that's going in the x direction, a delta that's going in the y direction, and you're convolving both of them with my x. This is something that actually seems to be stable in 2D. We don't know how to prove this, and understood Sinan also doesn't know. And I think so, but nobody knows. And if you want any error guarantee of the type that we saw before, we completely lost, because what we have is anywhere h alone will already be larger than 3 here. So there's no way we can push it below 2. So we need, if one wants to prove that like this, one needs a completely different set of techniques. I'm not saying that's not possible, but and we have some ideas, but it's very difficult. So instead, okay, so we're doing something that needs an additional ingredient, and that what we need an additional ingredient is that what is called a directional finite difference. So what we're doing here is we're saying we could do finite differences along the lines, along the columns, but we could also do it along the diagonals, right? And then we can set up the sigma delta scheme also along the diagonal. Like, of course, if we do it like this, we can run it the same way. It will give the same line artifacts. They're now just running along the diagonal, right? So still a good problem. But the trick that we're doing here, that we see we have now this the vertical, the horizontal, and this diagonal, and we saw if we sort of concatenate them, then it's very hard to do a stability analysis. So the idea that we had is let's just average them. So and that gives us a formula like this. You have these finite differences along the various directions, and you're averaging with a certain amount of weights. And other than that, you're just doing everything exactly as before, except that now that you have this weighted average of these different things with a certain amount of weight matrix. And you see already that this has a similar appearance to the picture that we've seen before. So we have sigma delta schemes that go along all these different directions here, and we're taking a weighted average of them. Yes?
That is my thing, that you didn't see the last line of the previous slide.
This one here. This is
the first reference, first step. There was a 2002, something like that. There.
This reference. This is a paper based by, sorry, it dropped down. It's a paper by Wrong Wang and her PhD student on sigma delta for images. I think we have it on the last slide, so you can see there. So, pardon? Yes. Yes, I don't know. So it's something. Look, I tried to change it. Yes, I think that something was. Yes, sorry, my bad. And so, yeah, I was changing the style somehow, and then I guess that happened. Sorry. So that we are. So this is now the theorem here. That we're just saying basically. If we're having a weighted combination of these sigma delta schemes along the different directions, we are also getting a weighted a weighted error, and that has sort of this error that we've seen before with some weight constant CW that's given in this form here. I mean, that doesn't tell us very much, but what we are yes, so this doesn't tell us very much, but we will explore this. I think right now I should check that I'm not losing. So here, let's assume explore some weight functions. So here we're having the 2-direction average scheme. So if we are just going vertically and horizontally, we're seeing that the weight function is 0.7. So I mean, just I don't know if I have it here. If we're going back to the, like I haven't put it, if you're going line by line, the weight constant is 1, right? So we have already some significant improvement by just doing the 2 directions. And then the next thing that we notice is that actually the Floyd-Steinberg scheme is a weighted sigma delta scheme in the sense of the previous definition, and the weight constant is 0.64. So it actually really improves upon this very simple combination. But the question is this actually desirable? And that's something that we will see here. So we're setting up this optimization problem, saying, let's solve this weight constant. And what we see is we get the optimal weight is, the optimal filter is something like this. It has like one positive, like one non-zero entry, like exactly here on the left, one step left of the bit that you want to calculate, and then one other non-negative entry that's as far as possible from in the other direction. So this is due to the fact that like you have to see that like there's no advantage in spreading the weights over different positive things here in terms of weight constant. The only advantage that you have is when you have a negative constant, and then you want to choose the one that is sort of has the largest negative, and that's what's here. So yes, okay, one could see that's something that comes out of this calculation, and let's bear this in mind because there's something to be checked if this is a proof artifact or if this is actually in the theorems, and so or in the numerics as well. So let's see. So the definition here, let's go. But first, before we do that, let's do the same thing with higher orders. So we're taking higher orders over different directions, and then we're averaging them just in the same way as we've done before. And this is, I think we will later on we will just do this at most with order 2, but for the difficulties that we have before. So this is the advantage for order 2 here. You're taking this filter here. This is a filter. This is actually a filter that is of second order in the sense that it's the second order finite difference of some finite length signal, and it has over this very short length, it has a nicely controlled L1 norm. But you can see it's still significantly above 1. I said you cannot go, you can get close to 1, but you cannot go to 1. So let's keep this in mind. So this is what we can use for second order schemes. And then the second order scheme somehow looks like this. You're having a 2-direction average scheme. For example, here that's the simplest. You're taking the second order scheme over the horizontal and over the vertical direction, and then you're just averaging them with weight 1/2, and you're again getting a weight constant of 0.7. But of course, now you're getting it in front of the error bounds for the second order, which are better. So let's see. And then we can also get the result here for the corresponding result for higher order, which is just sort of very much analogous to what we've seen before. And now this is, as I said, the interesting thing where we have to be very careful, because we have the filters that are going along the various directions. And what we need is that the weighted average of the L1 norms of the filters in the different directions need to be plus the amplitude of the signal need to be bounded by 2. So given that all the h's, if we're looking at higher orders, need to be larger than 1, we potentially have a problem given that that we have to restrict our y to be something less than 1, which is not ideal for images, let's say. But if we get to images in a second, I think. So before that, let's go back to this function case where we just, in order to see what our theorem says, in particular, to answer this question, is this weird filter of having 2 very remote locations and 0 otherwise, which doesn't seem very intuitive. Is this actually correct? Is this actually really a better thing? So we just set up a band-limited signal like this, and we here we're just running some experiments, and what we see is if you look at the pictures here, so you see the worst, I think here, the worst error is the first order row by row sigma delta scheme when you just go row by, not so very surprising. But and then somehow they all aligned. But interestingly enough, what's the best? The best here with the smallest error is really actually this scheme where we have these 2 remote entries with lots of zeros in between. So that at least surprised us, because it seems very counterintuitive to do it like this. If we sort of throwing away all the power and just putting some 2 remote entries there. So let me see if I did. Yes. So then for second order, I think it's hard to see, but the scale is much smaller. So you can see that for these band-limited signals, whatever if we're using second order schemes and average them, that it performs much better than what we've seen on the left. So, but of course we want to do this for digital images. We don't want to have a smooth function of that type, but we want to sort of use this for images. And so let's set this up. And I think this is the point that I would like to stress on. We have to use some type of stability constant. So because we have this problem that the H is in L infinity norm or in L1 norm larger than 1 and has to be, we actually see this in getting occasional instabilities that blow up the system. And it just, for some reason, this can be addressed very well by just doing a minor rescaling of the image by a very constant, very close to 1. That gives us a little bit of never true, like it doesn't satisfy the results, but still, for all practical purposes in all the experiments that we did, that sufficed to do stability. Other than that, this is the only thing I think that I should mention. Other than that, it's just how to implement this. I don't want to go through this, given that I have only 2 minutes. What I would like to show you, rather, is now we're looking at, does this actually work for images? Because in the end, we want not just to, I mean, it's nice to understand and to get a theory and maybe some results that explain why Floyd-Steinberg works, but can this actually help to improve things? And the question is, what is for images, what, like, having the signal to noise ratio is maybe not the best measure to say whether, because the signal to noise ratio, then how do we measure it? Because it will not be close. So what we used instead was the so-called feature similarity index, which is a state measure for image quality. We're just saying, do these images look alike? There's a score, and it has been computed, and we're just doing this for all these schemes. And you see that like 1 is best. And you see here that what we have, if we look at both for grayscale images and for RGB images, the second order weighted sigma delta schemes that that we have designed outperform all these other like standard, at least the simple error diffusion schemes. There are some schemes that actually solve discrete optimization problems to optimize the FSIM, but they are not tractable for real size images. So, but if you want to sort of follow the simplest approach of, there have been different weight matrices proposed sort of ad hoc in the engineering literature for these purposes. Here, our sigma, then sort of the theory gives us something that is actually better, which was a very nice we found. And as I don't know to what extent this is visible here on the screen. So it's very difficult to see here. There is, if we zoom in to this picture, you can see in the true image, there's one very visible hair here, or is it grass or hair? I don't know what exactly. I think it's one of the whiskers here. And then there's the second one that is very faint. And we can see that in the first orders, average sigma delta, you cannot really see it or it's broken. Whereas in a second order scheme, it actually shows up as such. So it also, in terms of sort of capturing fine details, it outperforms the previous methods. Yes, and with this, right on, like I have also the 10 seconds that Mark had. I would like to thank you for your attention and welcome any questions that you may have.
Thank you very much, Felix. Are there any questions? Raya.
So I'm also a little confused about the weight being sparse and acting over distances, in particular because I can see why that would work for a band limited function, but for an image that might have edges. Absolutely.
So that's sorry, I was, because I wanted to get a stopping time close to Mark. I sort of brushed over this. If you see here in this quality measure, like the opt4 suddenly is much worse than all these things here. Like the one that did best for band limited signal, where it sort of was designed to optimize this, is not doing well at all here and here. And this basically tells us, that's what I was mentioning in the very beginning, that it is not a perfect model to work with band limited signals. But sorry. But that's what we found so surprising, that still motivated and driven by this this band limited model, we actually get classes that contain interesting examples that outperform some of the things, or at least what you lose from the model mismatch is less significant than what you gain from going to second order. Maybe this is the way to put it.
Thank you. Are there any other questions from the web? From the squares? Somebody? No, the squares are gone. Okay. So then we thank Felix again. Wish everybody a nice evening.
Yes, before everybody leaves, maybe let me just make a couple announcements. So tomorrow we start with 2 talks in the morning that are online. And then there will be in-person talks here. I mean, I will be here, in fact, for the online talk. I guess it will be fun to sit here and watch them as well. So, but you're welcome. So the first. So let me tell you. Here are the first 2 talks tomorrow. First at 9, and it will be by Götz Funder, and the second by Rima Aliferi at 10. And there'll be coffee break. Then Casso will be in person right here at 11:20. And then Ozgur Yilmaz will be here at 14 in the afternoon. That will be they'll be in person. But I think for me, it will be comfortable to come here in the morning and hear the online ones also here. But it's up to you whether you'd like to be here or not for the online talks. Okay? Thank you very much. And we will see you tomorrow. No, I don't think so.
Thank you.